Hi guys, this morning's session. Superposition circuit with a current source, we did that tail end of last week, so we'll be skipping over that. We covered that, okay. And we're going to look at, first of all, Thevenin's theorem. Going to sort of kind of split the session in two, really. And then after that, have a look at Norton's theorem. The complex annotation for AC analysis, we might fit that in today. That might be where we start next week. Okay. This is based on what we did last year, and that's kind of, well, I'm working a slightly different format this year. So, right, Thevenin's theorem. The words: any active network having two terminals A and B can be replaced by a constant voltage source of voltage B, an internal resistance B little to resistance. The value V by that on resistance. But signs rather super. The best way to get is to do, okay, to do the Thevenin's theorem. First of all, the first thing to do is to remove the required load resistor for which and or voltage. So you'll open circuit voltage is equal to your Thevenin voltage or current, and V value equal to R to find the current. And a series half only like So, example. Big by way of a bit Theorem to calculate the current flowing and the power dissipated in the 30 ohm resistor. Okay. So first thing to do is remove the 30 ohm resistor and find the VOC, V open circuit. That V circuit, remember, is equal to the Thevenin's voltage that we want to use. Okay, so what's the plan of action to find that open circuit voltage? What are you going to do? Sorry? So you're going to find the total resistance of that circuit as it stands. What are you going to do with that? What will that help you to find? What can find an RT help you to find? Which current? Current don't go across anything. Current goes through. Is the total resistance going to help you find that current? That current? Or that one? Yeah, that'll find you I1, won't it? Yeah? What's the value of that current? Okay, I'll give you that. But what is its value? Can you tell me what value it is right now? In amps? Who said? Why? Because that part of the circuit's open circuit. There is zero current for that resistor at that moment in time. Yeah? So, actually, by finding I1, you're going to find I2 as well. Okay? So you can find I1, I2. What would that allow you to do? We want to know when the resistor's connected, right? When the 30 ohm resistor's connected, the current would be in that direction, and so that voltage arrow would be that way. How can I find from those two pieces of information what VOC is? What's the volt drop across the resistor R1 in the condition? current going through the resistor, no volt drop across. So this volt drop is also 0 volts. 0 volts. No current through. So how can I find now VOC? I'll rephrase that. How can you find VOC? Worry about doing it for a minute. Just worry about how you're gonna do it. Find RT, don't you? You know how to find that using Ohm's law. Think Kirchhoff's laws. If you know the current I2, what can you find? Voltage across. Yeah, you can find this voltage across here. What direction is it, Curtis? So the current's down, voltage is up, VR2. Now what have we got that will help us find this? And I'm trying to help you understand why VOC is the value it is. It's in parallel. The key to this is that there's no current through that resistor. We've got a Kirchhoff's voltage law loop around there. How does that work? I mean, I'm not interested in values at the moment. This is VR2. There's one voltage. There's another one equal to nothing, but it could be there. There's a complete loop, isn't there? What does Kirchhoff's voltage law say about a complete loop? I always said you can find VR2. How does that help us find VOC? How do we deal with Kirchhoff voltage law loops? Right? Remember them back to science. You did something with the arrows. No. No. Do you remember saying all Kirchhoff's voltage law says the sum of all the voltages around a loop add up through the arithmetic sum. But we looked at them in terms of clockwise arrows and anti-clockwise arrows being equal, didn't we? Do you remember that now from science? Okay. We've got clockwise arrow there, VR2, and two anti-clockwise arrows, VR1 plus VOC. That's equal to nothing. So surely that's gone. That's VR1. VR1 is equal to nothing. So VR2 and VRC, because there's no current for them, they're equal to each other. So that is equal to VOC by the fact of whatever other tools you've already learnt and have available to you to find that open circuit voltage. Might find that voltage from last week. The position. Yeah. Okay. Open circuit. Right guys, how do we go here? RT is equal in this instance. 5 is R1. Oh. R3 don't exist, we're taking R3 out. But we're looking at the resistance to this battery. And this current flow currently going around there. And we've already, there's no current going there because that's open circuit. So looking from this battery, what's the resistance equal to? Just a series circuit is the only current in there. So at this point in time, the total resistance of that circuit to that battery is those two resistors added together. 5 plus 20 equals 25 ohms. Completely different circuit if we put the 30 ohm resistor back in, but at this current moment in time, at this instant in time, that is the total resistance to that battery. Yeah? So if you know that, how would you find the current? There's only one current. I1 and I2 are the same current. VS resistant, that's 20. I automated it at 25 volt. And then the yes. Thevenin's voltage of our equivalent battery. So just there's a couple of pointers. Right, so you've got to look at what resistance there is to the currents that are flowing and use that to calculate your total resistance. Ignoring the leg, which is open circuit, because there's no current flowing in there. Alright? Just be careful with that. Right. Yes. Any and I've replaced it with a so I know I'll put just or just drawing it around the volt source. I calculate what the resistance is looking back in here. An ohm meter, that's those two terms. Current flow, ohm meter, current. Some go down there, resistance wise. Our Thevenin is that looking back in there. How can I calculate that? I've got parallel. It's not all parallel, is it? R1 and R2 in read in series. R4 comes in. No. Thevenin's was 19.2, wasn't it? The bit here in green is acting like that network with the voltage source in it. To any load that you put on the end there, you've just so Thevenin's done. Find the current. Very simple series circuit. Then we could also use it for a 20 ohm resistor, 100 ohm load resistor, so on. Just V squared. Use I. Still get the right answer, and you'll be doing extra work. Surprised. The procedure to press the look to look at terminals. Last week using, see if we get if you hold the cap you can do, can't you? Take the open, take V1 out, you'll have a current I2 going in that direction. Which what I on this same page because this side is 1.09, so 1.09 amps. Therefore, the total current flowing in this circuit is in that direction, and it's 0.181. So the current of that current I1. On these two resistors, R1 and R2, where we know the direction of the current. It feels them. I'm going to find VR1 a 6 ohm resistor. This loop now now, help me. Equal to six times 5 over so now Thevenin's equivalent, like so. With R Thevenin's equal to 2.73 ohms. IL V Thevenin's over R Thevenin's plus RL 10.9 over 32.73 equals. And does that match with what I'm? The current by 3. Yeah, I wouldn't. 0.1 of an amp different, depending on. Well, yeah, on how clear. Considering the kind of round we've been doing, the figure not out of the way. Okay. So that's Theorem's theorem.